Hello and welcome to Dr. Jim's Structures class, where we do structures by example.
Man's practicing fuzzy math again.
Thanks for tuning in. In a previous video, Dr. Jim used hand calculations to draw shear force and bending moment diagrams for this simply supported beam. This video shows how to check the hand calculations using LinPro. If you want to watch the hand analysis video, then click the link on the screen. LinPro is a free, lightweight, graphical, easy to use frame analysis program. Dr. Jim recommends downloading a copy of LinPro from the web, or alternatively, get yourself over to Dr. Jim's website at drjimsstructures.com and download a copy from there. There's a link to the website in the description. This video will focus on the application of the uniformly varying load, the UVL, and will spend little time on other aspects of the analysis. You are assumed to be familiar with the basics of using LinPro, and if you are not, then you are recommended to watch Dr. Jim's introduction to LinPro before continuing. There's a link to that video on the screen. LinPro offers both keyboard and graphical input capabilities. We will use graphical input where possible, as it's quicker and less error prone. Start by considering the units to be used. LinPro's default units are kilonewtons and meters, and these happen to coincide with the units used for the hand calculations, so leave the units as they are. Next, define the grid. Click the grid button to open the grid dialog box. The beam is 6 meters long, so set the width of the grid to 6 meters and set the height to 2 meters. Leave the grid spacing at 1 meter and the structure will be built at a height of 1 meter. LinPro's terminology differs in a number of ways from the more generic finite element terminology used by other structural analysis programs. This video makes use of both LinPro and finite element terminologies. If this makes little sense to you, then you can find out more about LinPro and FE terminologies in Dr. Jim's video on using LinPro to analyze a pin-jointed frame. There's a link to that video on the screen. Having defined the units in the grid, the next step is to define the nodes. But before continuing, we must decide how many elements will be used to build the mathematical model of the structure. Looking at the space diagram of the structure, Dr. Jim's first thought was to use 4 elements to represent the beam. That would require 5 nodes. His second thought was to use a single element requiring 2 nodes. Dr. Jim's life experience has shown him that his first thought is often his best thought. But here we will go with his second thought and use only a single element running between points A and E on the space diagram. To add these nodes, right-click on the workspace and select the joint pointer. Yes, Window uses the term joint rather than node to define points in space. Now add the nodes by clicking in the workspace. Note that the pointer coordinates are displayed in the bottom left-hand corner of the window, and that the coordinates snap to the grid, making adding nodes simple. Next, right-click and select the member pointer. Notice a dialog box pops up showing that we are entering Type 1 elements. We have not defined any element types, so we are using the predefined LinPro element. If you are curious about the default LinPro element, then you can find out more by clicking the link on the screen. Click on node 0 to define the start of the element, then click on node 1 to define its end. Right-click in the workspace and select the pointer. Next, right-click on node 1 and select vertical support to add the roller support. Note that in finite element terminology, supports are referred to as restraints or boundary conditions. Now click on node 0 to select it, then right-click and select pin support. The structure has been defined in double quick time. All that remains is to define the loads, so let's get on with it. We will start by applying the uniformly varying load, the UVL. Click on element 0 to select it, then right click on the element and select the Add Load option to open the Add Load dialog box. Note, LinPro can deal with multiple load cases, and LinPro always predefines an empty load case called load case 1. By default, the dialog is set up to add a distributed load acting in the global Y direction to load case 1. The UVL is a distributed load, so leave the load name as distributed. It's not obvious how to proceed, so click the hint button to open a dialog box giving information about the values to be entered. We see that A and B define where the load is to be applied, and P1 and P2 define the intensity of the load at its ends. These values allow a lot of flexibility when defining distributed loads. P1 is the intensity at the start of the load, so leave the value at 0. P2 is the intensity at the end of the load, so enter -90 for P2. This value is negative because the load acts in the negative global Y direction. Clicking the absolute button shows that LinPro offers 3 ways to define the distances A and B. Here we will use absolute values. That is, actual distances will be used. The other options are explored in the video linked to on the screen. A is the distance to the start of the load, so enter 2, and B is the distance to its end, so enter 4. Then click Apply. LinPro shows the load graphically in blue. The diagram shows an arrow pointing downward and an intensity of -90 kilonewtons per meter. Yes, really. Dr. Jim hopes an alarm bell has gone off in your head. A downward load of -90 is the same as an upward load of +90. To fix the diagram, either the negative sign should be removed or the arrow should be turned around to point upwards. Think about it. LinPro is good, but it's not perfect. Dr. Jim's advice is to ignore negative values on all graphical representations of loads and reactions. It's annoying, but just live with it. All that remains is to define the point load. Again, right-click on the member, select Add Load from the drop-down menu, then click on the Point Load tab. Leave the load name at Point, as there is no good reason to change it. Next, click the hint button to get more information about the values to be entered. Note that the coordinate system is set to global. The global axis system has a horizontal x-axis, a vertical y-axis, and a z-axis that points out of the screen. It is a standard right-handed axis system. Changing the coordinate system to local changes the coordinate system to that of the element. We see that the element uses a right-handed axis system and that the element x-axis runs from node I to node j, where node I is the first node selected when defining the element. The element axis system for element 0 coincides with the global axis system, so it's immaterial which system is used to define the point load. We'll use the element axis system, so leave the coordinate system set to local. The hint dialog box shows that A is the distance from the start of the member to the load, so enter 1, then enter 120 in the force Y box. Clicking the Apply Load button applies the load, and again LinPro helpfully shows the load on the diagram. This time there's no confusion regarding signs. The structural model is now complete, so click the green arrow to run a linearly elastic static analysis. It's super quick, and LinPro draws a structure showing the displacements caused by the loads. Next, check the reactions by clicking the R button. Woohoo! They agree with the hand calculations. Clicking the M and T buttons shows that the shapes and values on the moment and shear diagrams broadly agree with the hand calculations. but Dr. Jim thinks it's too early to declare victory because the diagrams don't show enough in numerical values to make an effective check. The shear diagram looks like it agrees with the shear diagram from the hand calculations. To double check, click the Numerical Results button to the right of the green Analysis button, then click the U and F along member tab. By default, LinPro calculates displacements and internal forces at 11 equally spaced intervals along each element. In other words, it divides each element into 10 equal intervals. Inspection of the shear values can't conclusively prove that the hand calculations are correct, but there's nothing to suggest that the hand calculations are wrong. The easiest way to make a stronger check would be to plug 3 meters into the expression for shear in the hand calculations to show that the shear 3 meters is minus 37.5 kilonewtons. Now close the numerical results dialog box, then click the M button to display the bending moment diagram. Reopen the numerical results dialog and again click the U and F along member tab. Both Dr. Jim and LinPro draw bending moments on the tension side of the elements, so the bending moment diagrams agree in shape. However, inspection of the LinPro diagram shows the bending moment at B to be minus 60 kilonewton meters, whereas it was calculated to be plus 60 kilonewton meters. This is not a problem, it simply means that LinPro and Dr. Jim are using different sign conventions for internal moments. Such apparent contradictions are very common in structural analysis because sign conventions are conventions. There's nothing absolute about them. Indeed, later in this course, Dr. Jim will dispense completely with putting signs on bending moment diagrams. This is because drawing bending moments on the tension side of the members is the sign convention. It's simple, elegant, and totally unambiguous. Returning to the numbers, the hand calculations found the maximum moment to be minus 65.32 kilonewton meters, 3.365 meters from the left-hand support. And taking the difference in sign conventions into account, inspection of the moment column indicates that 65.32 is reasonable, and Dr. Jim is happy to tentatively declare victory. If you're still skeptical, then try plugging 3 meters into the expression for moment that was developed in the hand calculation. A result of minus 52.5 kilonewton meters would be a strong indicator that the hand calculations are correct. Before closing, it is worth noting that we can now add 3 new rules to our universal truths about shear force and bending moment diagrams. 1. Shear force diagrams are parabolic under UVLs. 2. Bending moment diagrams are cubic curves under UVLs. And 3. Maximum bending moments under UVLs occur at points of zero shear force. Well, that's all for today. Thank you for watching. If you found this video useful, please give it a thumbs up and consider subscribing to Dr. Jim's Structures channel. Bye for now. Hope to see you again soon.